All right, so part 2 of the transformations, still on 6.5, so we're still talking about transformations of the sine function. In yesterday's lesson, we compared graphs that had the c and the d value, right? So we looked at having these added into a function and how those transformed your function. All right, so compared to the graph, f(x) sine x minus c plus d is translated to blank by c units and blank by d units. So right, left, because that's what the c deals with, and then up, down is what the d deals with. So today we are going to investigate what the sine function does when you have a number other than 1. So remember I was saying yesterday how you can kind of look at the sine and you can see, oh, well, there's a 1 here, right? Well, what we're going to look at is what happens when this number that's in front of the sine is not equal to 1, okay? Well, think back to your quadratics again, right? I keep making this comparison because it's identical. It literally is identical. So, in yesterday's lesson, we talked about this h and this k. Well, now we're looking at this a value. So if you think back to your quadratics, that a, well, that was your vertical stretch, your vertical compression. And remember, if you saw, let's say, a minus 2, right, x plus 3 squared plus 5 or something, this negative, remember, that was a reflection. So we will see that. You're going to see, like, we're going to go through our investigation here, and we're going to see what happens when we have these negatives. What happens when we have these numbers bigger than 1, numbers that are like a fraction, okay? So just like we started in the last lesson, let's start by graphing our parent. Remember, this is the parent, and get used to just memorizing these values, okay? So 0 degrees, your sine function is 0. 90, it's 1. 180, it's 0. 270, it's negative 1. 360, it is 0. So plotting that, and I guess let's label our curves. So 1, 2, 3, 4, and 5. Negative 1, negative 2, negative 3, negative 4, negative 5. Let's give each tick on the horizontal 30 degrees. So 30, 60, 90. There, 1, 2, 3. This would be 180. 1, 2, 3. This would be 270. 1, 2, 3. This would be 360. Okay. So let's plot our parent, 0 degrees and 0, 90 and 1, 180 is 0, 270 negative 1, and 360 is 0. So your parent, as always, looks like this. Okay, that's just the nature of that function. Well, what happens when we have a value, so remember this has an a value of 1 here technically, what happens when we make that value 2? Well, mathematically what happens is you say, okay, we'll still evaluate a function at 0 degrees. You're taking 2 and you're multiplying the value of sine at 0 degrees. That's 2 times, what is sine at 0? 0, so you do this math first. You do, what is the sine of 0? You then multiply the 2 and you get 0. Right? So let's do one more time. This is the function at 90 degrees. So this would be 2 times the value of sine at 90. So that's technically 2 times. Notice I'm not multiplying the 2 into the 90. It's just 2 times sine 90. So I evaluate this. That is 1. And I get 2. So 2 times, what was the value of 180? The sine of 180 is 0. So 2 times 0, 0. 2 times negative 1, negative 2. 2 times 0 is 0. Let's plot those points. So remember, you're creating ordered pairs here. So at 0 degrees, you're at 0. 90, you're at 2. So if we plot these points, 0 here, 90, you're at 2. 180, you're at 0. And 270, you're at negative 2. And 360, you're at 0. So there you are. You're up here. You're down here, and over here. And before I add another one, because I don't want to add the third graph and make this look messier, this is not a vertical shift. It might look like a vertical shift because you're like, oh, well, this point right here is 1 unit up, right? But no, you'd have to have every single point. Like you'd have to have this point right here. It would have to look like the point up here and the point down here. Like both of these would also have to go up by 1. But all that's happened is you have these certain points that have been stretched up. Like it's this, your function is being pulled on either end and it's being anchored here still at on the axes. It's being pulled up and down. There is a vertical stretch on it. And let's see what happens when we do the half. So same math, you're evaluating at 0 degrees. It ends up being a half multiplied by what is the value of sine at 0? Well, that's 0. So half times 0, it gives you 0. Half times the value of sine at 90 degrees, which is 1, would be 1 half. 1 half times the value of sine at 180 would be 0, would give you 0. 1 half times the value of sine at 270, negative 1, gives you negative half. And then half times the value of sine at 360, right? I'll just write this because I didn't write it for anyone, but you're saying still sine at 360. So that's still 0 then. So if we plot those points, it's going to get real tight in here. You're going to have 0, 0 still. 90 degrees, you're actually going to be at half. So you're kind of like down here. But notice how you're still plotting this first point at the same point right here. And these points still line up. You're not shifting or anything. But you're just like, you're kind of squished. You're kind of sat on it. 180, you're 0. Negative 1, you're here. And then 360, you're here. So your graph looks all very flat, okay? Because it has been vertically compressed, just like what happened in the quadratic unit. So this one right here is a vertical compression. This one right here is a vertical stretch. That's because your A is bigger than 1. And I should have added that here. Your A here is key thing. It's between 0 and 1, right? Like that's how you notate that. Annotate that. Complete the following table and values and then graph the given function on the grid below. So now in this case, look what happens when we make the A here. The A here is technically negative 1. That's what that negative is there. So the math, this first column, this is still our parent here. So if we plug them in, it's still 0, 1, 0, negative 1, and 0. So if we add our points here, 1, 2, 3, 1, 2, 3, make each tick 90 degrees, so 90, 1, 2, 3, 180, 1, 2, 3, 270, 1, 2, 3, 360. If we add our points here, we'll have 0, 0, 90 and 1, 180, 0, 271, 360. So this is our parent function, okay? So I'm just kind of going through this quickly because we've done the parent so many times. But now we have this A of negative 1. So you're still valuing the function at 0 degrees. So you have negative sine of 0 degrees. As always, evaluate this first. That ends up being negative times 0, giving you 0. So this would be negative sine of 90. That would be negative 1, giving you negative 1. This would be negative sine of 180. That's negative 0, giving you 0. This is negative sine of 270. And again, sine of 270 is negative 1, right? Like that's what the parent is. So that's negative times negative 1, giving you 1. And then this negative sine of 360, well, that's negative times 0, giving you 0. So at 0 degrees, you're at 0 still, so right here. But now when you're at 90, oh, I should have put negatives here, negative, negative. At negative 90, you're at negative 1, right here. At 180, you're at 0. And then 270, you're at 1. And then 360, you're at 0. So notice, typically on a sine graph, you go up first, right? You head upwards. Well, now we are going down first. That's because we have like essentially taken that sine and we have flipped it. So notice how like, you usually go up, we're now going down, and we get to this 80, and then once you get to 180 on the regular sine graph, you start heading down, but we're doing the opposite. We are now heading up here and down. So you kind of get this wave, and that actually is what a standing wave is in physics. That's what sound looks like. So it has a reflection. So when the A, if this is a reflection over the x, that's because A is negative. So the value of A, well, the value of A here in this case is this what you're looking at in the beginning of the function. So this is 1. This one is 2. This one is 1/2. This one is -1, right? Well, remember what I said in the previous lesson, the amplitude is just the value of your A here, right? You can prove it, max minus min over 2, right? But the amplitude is just the value of the A. And actually, specifically, it's the magnitude of the A. So it's taking into consideration not what the negative is. I don't care if it's negative, because all it is the distance between the two. So you purely just look at the number of A. You're purely just looking at the number you see. So it's 1 in this case. It's 2. It's half here. And this one is 1, not -1. Okay, because this -1 right here, remember that was this graph right here, this blue one that we drew. Look at the distance, right? It's a distance of 1 here to your center line, 1 here to your center line. So your max is still 1. Your min is -1. So if you still go 1, take away -1 over 2, you still get a value of 1, because the amplitude is a value of 1. And remember what I said on all the other graphs, right? Your period never changes. This right here is the same. It does not change on any function. It will always be 360 degrees, right? But let's look. See here, you're starting at 0 degrees, and you go all the way over here, and you finish your pattern, still at 360. Let's go to our previous ones where we had all those other transformations. Right up here, it's 0 degrees, and over here, still at 360. So it still takes you 360 degrees to complete one cycle. So your period is still 360 for every single one of these. This is 360, this is 360, and this, the reflection is still 360. Okay, well, your domain never changes. In the previous lesson, I talked about that. All of these are x belongs to real numbers, okay? So I'm just going to put this here so we can add more space for a range. They are all x belongs to real numbers. Your range is your y values though. Okay, so remember, your range talks about your min and your max. So ask yourself, when I have these stretches and compressions, am I changing the value of my maximum? So another way to think of it is, are my amplitudes any different here? Because remember, those are the distance between max and mins. And yes, your amplitudes are changing. So that means, and visually, let's go look, we can see, yes, your max and your mins are changing. Look, here you have a max of 2. Max of 2. And on the one that was compressed, here you have a max of half. So when we report our range, right? So the parent one is always the same. Its range is y belongs to real numbers. And you're always going to be between these two values on your parent, the one that doesn't change. But let's look at the one that had a vertical stretch of 2. Your range, what is your minimum? Well, you're all the way down here at a minimum of -2, and you have this max of 2. So you are between -2, y, and 2. Let's look at the one that was vertically compressed. Well, what is its minimum and maximum? So that's this one right here. Well, its max was half, and look at its minimum right here. That corresponds to a value of -half. So min of -half. So that's where your graph is oscillating between. So here it's -1/2 less than y less than 1/2. And then this one, your amplitude is still 1. That's the same as your parent. So because your amplitude is the same, it won't change your max and your min. It's going to be identical still, right? Sorry, I say that if the amplitude is the same, that's assuming there is no d value, okay? Because there's no shifts up or down. So you have to account for that, but these have no shifts, they're up or down. But you can visually look at the graph right here, the one that has the reflection, and notice how here we have a max of 1 and a min of -1. So your range here, your range on this last one, is the same as the parent. Okay, so when you have a value, that is going to represent a vertical stretch. Compared to the graph A represents a vertical stretch / compression, and I guess I ran out of room, and reflection. Okay, it deals with 3 things. So when the A was bigger than 1, it was a vertical stretch, and you say by a factor of A, whatever your A is, and then when the A is between 0 and 1, it's a vertical compression by a factor of A. And then the last one, when your A is negative, it's a reflection over the x-axis. So we have 2 examples, right? So example 1, for each function, so we only have 1 function. Describe the transformation, sketch a graph of each, state the period, amplitude, and the equation of the axis, state the domain and range. So for each function, describe the transformations. Let's start with sketching the graph first. So if we're sketching the graph, whenever it says sketch a graph, use the mapping notation, okay? So that's why we showed in the beginning, or I showed you in the beginning, what the different transformations have and where to put them on what variable. So overall, your mapping notation, well, we looked previously and we said, okay, well, x plus c, and then it's a y, same as quadratics, plus d, all right? So when we look at our function over here, our a is -1/2, here our d is 5. So if we plug that into our mapping notation, we're going to have x, no c value, but we'll have -1/2 y plus 5. And so then create your table values from your parent function, and then we'll apply the mapping rule to these points. So we're getting the points y equals sine x. This is our parent. So 0 degrees, 90 degrees, as we filled in all of the tables above, 270 degrees, 360 degrees. This is 0, 1, 0, -1, and 0. And now if we apply our transformations, right, using our mapping rule, we have x that has no shifts on it, so we're literally just going to copy down the same points that we use because they're not being transformed at all, so these are still the exact same degrees from your parent. But now all of your y's are being multiplied by negative a half, and then you're adding 5 to them. So I'll show you the first math here. This is negative 1/2 times 0, and then you add 5 to that. So you do this first. So negative half times 0 is 0. Add 5, and you get 5. So do that for the 90. So you'd be going 90 times negative half, and then add 5, and you get 4.5. Do 180. So you'd be plugging in the 0 here into the y, and you get 5. This one you get 5.5, and then 360 you'd get 5. So these are your new coordinates. These are what you're going to graph, okay? 0 degrees and 5, 90 degrees 4.5, 185, 270, 5.5, 360, and 5. So let's make our axes. How many ticks do we have here on the vertical? 1, 2, 3, 4, and 5, and we need to go all the way up to 5.5. So what I might do then is I might make each one of these a value of 2 instead. So 2, 5, 6, and 8. Yeah, that'll go through. Okay, and then -2, -4, -6, -8. All right, and then let's label our horizontal. So the horizontal, to make each one of these ticks 30 degrees. So that would be 30, 60, 90. 1, 2, 3. This would be 180. 1, 2, 3. This would be 270. 1, 2, 3. This would be 360. Perfect. Okay, so plotting the point 0 degrees and 5. So that'll be, I'll do it in blue. 0 degrees and 5. 90 degrees and 4.5. So 90 degrees, 4.5. That would be like halfway between these two. And then we have 180 and 5. So right up here. We have 270 and 5.5. Right there. And then 360 and 5. Right there. So connect those points. There we go. Perfect. So we've graphed our function. This is f of x. This is that new transform function. And now let's describe the transformations. Well, we can see that it is reflected. We can see that there is a reflection over the x. All right, because it's flipped upside down. Usually you go up first, but we don't. We went down. And then you have a compression, a vertical compression. By a factor of 1/2. Then you have a vertical shift up by 5 units. All right. State the period, amplitude, and equation of the axis. Well, this next part, 3, so I, well, the period is always 360, so the period equals 360 degrees. But we can also just see that. Look, it go from here all the way to right here. This is 360 degrees. All right, well, the amplitude is a distance. Remember, it's the magnitude of your A value. So we said our A was -1/2. So that means this would be the magnitude of -1/2, which means just 1/2, right? But it's also, you can see, I'm going to jump ahead and show you the equation of the line. Your D value here being 5, remember that gives you your axis here. So you have at y equals 5, right here. Y equals 5. Notice how far off you are to your max. So this point right here, remember this point is at a y value of 5.5. So you are a distance of a half off your center line. That's because your amplitude is a half. So your amplitude, so if you're A, so your amplitude equals 1/2. And then your axis, as we just showed, is the D value, so it's y equals 5. And then lastly, state the domain and range. Okay, so, well, the domain is always the same. It's x belongs to real numbers. But the range, so in this case, let's look at our graph. Our max, we have a max of 5.5 and a min of 4.5. So your range then is y belongs to real numbers, and you state your minimum first. So 4.5 less than y less than 5.5. There we go. Last example. The graph f of x equals sine x has been compressed by a factor of 1/2, reflected in the x value, over the x-axis, translated to the right 120 degrees, and 4 units down. Write the new equation. Okay, so we have a reflection. So that tells you your A is negative. You have a compression. So that says your A is 1/2. So just based off those two values, I can start by writing f of x is 1/2, but negative sine. All right, and then it says translated to the right. So then you have x, and if you're going to the right, this needs to be minus 120 degrees. And then this last part right here, and 4 units down, that would be minus 4. So you can see where all those key pieces of information came from. And there is your final answer. All right, I mean, let's just write it all with one color. F of x is minus 1/2 sine x 120 minus 4. All right, that is your new equation with all your transformations. All right, there's our homework, and I'll see you in class. Bye.